Hi everyone, my name is Aman Kumar. I am from IIT Aisham Dhanbad, currently pursuing Masters of Science and Technology in Applied Geophysics. Today we're going to see the simple harmonic motion, cu- especially the subtopic of simple harmonic motion, that is linear and angular SHM. So before we are going to explain linear and angular SHM, firstly let's briefly explain what is simple harmonic motion. So simple harmonic motion is a special kind of oscillatory motion in which restoring force is directly proportional to the displacement of the body from its mean position. So we can see that here displacement may be angular or linear. This means there may be two cases, either it's linear SHM or angular SHM. So we'll see ahead, we'll look ahead what is linear SHM and what is angular SHM. So firstly, let's describe what is linear SHM. When a particle moves to and fro motion about a fixed position called mean position or equilibrium position along with the straight lines, that is called linear SHM. For example, we can see that a spring mass system, when a spring is equipped with a block, there maybe, and we slightly displace the block, there arises the case of linear SHM. So there are some necessary condition for taking the simple harmonic motion. Firstly, the restoring force is directly proportional to their negative of displacement. Why negative? Because restoring force is always directed opposite to their displacement. We can see here the displacement of the block from mean position in positive x direction, and the force acting due to this spring is in negative x direction if we take x in this direction. So we can say that force is negative proportional to their displacement. So also we can say that acceleration is also proportional to their negative of the displacement, and this force is always acted towards their mean position, which means when they perform this block perform a linear SHM, let's suppose for some after some time this block comes here, and this block comes here, and for this the displacement is this one, and now force is in opposite direction. So we see that force is always oppose their displacement. So now from here we can write restoring force is minus kx, where x is the displacement, f is the restoring force, and k is a positive constant. So now from Newton's second law of motion, we can write ma equals to minus kx, and we get acceleration equals to minus k by m. And also we know the acceleration is double differentiation of their position. So from here we can write d square x by dt square equals to minus k by m into x, and we get the main differential form of linear SHM. We see that this type of for this type of equation for any SHM problem. So this is the general equation of this differential form, where omega is root under k by m, and omega is the angular frequency, and phi is the initial phase of this SHM. So after angular frequency, we can calculate the time period of that SHM. So we know time period is 2 pi by omega, and from here we also calculate omega equals to k by m. So when we put the value of omega in this time period, so we get time period is equal to 2 pi root under m upon k. So now we will keep this in mind, and for any type of problem we will try to make this type of equation, then we can calculate their angular frequency, and after calculating angular frequency we can evaluate their time period. Let's try with an example. Suppose this is a spring block system and we have to calculate its time period. So firstly, for this type of problem, firstly we will slightly displace the object and make its FBD, free body diagram. So we can see that for this there is a spring force which is act as a restoring force in this case. So we can write F equals to minus kx, and now from Newton's second law, we can write ma equals to minus kx and a equals to minus k by m into x. And from above, we can see that this type of equation comes, and from here we can deduce that omega equals to root under k by m, and from here we can say time period is 2 pi root under m upon k. Now, let's see the second problem. This problem comes in JEE Main 2023. So, firstly, let's understand that problem. So, this problem saying that of a spring constant mass of block is 490 gram, a spring constant k is given, and if the block is horizontally displaced through x meter, then the number of complete oscillation it will make in 14 pi second will be. Let's do that problem. So, firstly, I already make its diagram. So, let's suppose, so let's slightly displace the object and by x. So what is the restoring force acted on this block? So we can see that this kx, after compression of this spring, first spring, and extension of this second spring, both spring forces acted in the same direction. So we write F equals to kx plus kx equals to 2kx, and this displacement in positive x direction and force is in negative x direction. So we can write F equals to minus 2kx. So from here we can write ma equals to minus 2kx and a equals to minus 2k by m into x. From this we can say that our angular frequency is 2k by m, and our time period of this spring block system is 2 pi root under m by 2k. So question is to evaluate the number of complete oscillation it will make in 14 pi second. So after putting the value of mass and spring constant, we calculate the time period. So what is time period? Time period is making a complete time to take a complete one oscillation, and here calculate number of complete oscillation in 14 pi second. So firstly we will calculate time period, then divide it to 14 pi, and we will calculate number of oscillation. So number of oscillation equals to 14 pi upon t. So from here we can write 2 pi root under 49 upon 400, that is 2 pi into 7 by 20. After calculating this time period for calculating number of oscillation, we will put the time period value in this formula and we get something 20 oscillations. So here this is a NEET type problem. So if number of oscillation it will make in 14 pi second will be 20. Now we'll see the angular SHM. So what is angular SHM? Angular, we see from this figure, a disc is hanging from a wire. If we twist the wire in this direction, little bit twist, then and suppose here is a particle A, and after twisting this wire, this particle reaches at B. When we leave the twisting of wire, then this perform the angular SHM. This particle moves from B to A or A to B. So there is angular displacement with time. So what is the necessary condition for the angular SHM? So in this case, we see that main thing is what torque is applied. So the restoring necessary condition is the restoring torque and angular oscillation on the particle should always be proportional to the particle angular displacement and oriented towards the equilibrium position. So just take analogous from linear SHM. There we will see that the restoring force is directly proportional to minus x, or acceleration is directly proportional to minus x. Here the same thing will displace by torque. Torque is directly proportional to the angular displacement, and angular acceleration is directly proportional to their angular displacement. So from that, we will write torque is directly proportional to the minus of displacement. We also see that torque, direction of displacement, and torque in its opposite sense. So here torque is minus k theta, and we also know torque equals to I alpha. So when we equate I alpha equals to minus k theta, we will get alpha equals to minus k by I theta. That is same as we already seen in linear SHM, that is a equals to minus k by m into x, and we from here we get alpha equals to minus omega square theta, where omega equals to k by I. Here I is the moment of inertia of the body. Here I is the moment of inertia. So from here we will get the our differential form of angular SHM, and also we will see this type of equation. This is the general solution of this equation. So once we will get the angular frequency, we will get our time period, that is 2 pi by omega. So this problem comes in JEE Advanced in 2009. So here, firstly, let's read what will question says, and then we will solve it. So firstly, this question says a uniform rod of length L and mass M at the pivot is pivoted at center. Its two ends are attached to the two springs of equal spring constant K. The springs are fixed to rigid supports as shown in figure, and the rod is free to oscillate in horizontal plane. So this is in horizontal plane. The rod is gently pushed through a small angle theta in one direction and release the frequency of oscillation. So here they asked the frequency of the oscillation f, and we know omega equals to 2 pi f. So once we will calculate angular frequency, we'll reach to the frequency of the oscillation. So just slightly displace the rod from its position. Let's suppose we displace is through x, and then the force applied by a spring here is extension in the spring, so force is directed in this direction. Here is also extension in the spring, so force is directed in this direction, and both force rotate the rod in same sense. So firstly we calculate what is the total torque about this pivoted point. So this will in horizontal plane. So we know torque equals to r cross f, r vector cross f vector. So from this point, this force and the distance of the force from this point is L by 2, because the length of the rod is L. So and both the spring have same spring constant K, and these are identical, so the force is same. So torque equals to FL, and this spring force F equals to Kx, so we can write FL equals to KXL, and we also know torque equals to I alpha. And now we equate this equation, and we see that theta and torque are in opposite sense. They will rotate the rod in opposite sense, so there is a minus sign. And we know for a small angle, sine theta equals to tan theta equals to theta. And we also know if angle is small, let's suppose this is a circle of radius r, and this is arc length x. If theta is small, then we can write x equals to r theta. From here we can write x equals to L by 2 theta, and when we put into this equation, this is the x equals to L by 2 theta, and we know the moment of inertia of the rod from the center of mass is ml square by 12. So after putting this value, we get angular acceleration is this alpha equals to minus 6 k by m into theta. And from the above equation we will see that this is the alpha equals to minus omega square theta. We can say that our angular frequency is root under 6 by km, and once we equate it to the 2 pi f, we get our frequency of oscillation, that is 1 by 2 by root under 6 k by mm. So there is a C option is our correct answer. So thank you.